Welcome to the Bare Metal Cyber Security Plus podcast. This series helps you prepare for the CompTIA Security Plus exam with focused explanations and practical context. For a companion study guide, check out the Achieve CompTIA Security Plus 701 Exam Success by Dr. Jason Edwards. It is the most concise and complete Security Plus guide on the market, built for busy professionals who want to pass the exam fast and on their first try. You can find this book and others at cyberauthor.me. In this episode, we are examining application-level vulnerabilities, some of the most dangerous and difficult to detect flaws in cybersecurity. These vulnerabilities are not always visible from the outside, but can be exploited by attackers to compromise systems, steal data, or gain administrative control. We will focus on 4 key areas: memory injection attacks, buffer overflows, race conditions, and malicious updates. Let's begin with memory injection attacks. These occur when an attacker forces an application to load or execute code that was never intended to run. One common method is dynamic link library injection. In this technique, the attacker inserts a malicious dynamic link library file into a legitimate process. Once the file is loaded, it runs under the identity of the legitimate application and can perform unauthorized actions like reading memory, logging keystrokes, or redirecting data. Another form of memory injection involves pointer manipulation. In this type of attack, the attacker interferes with how a program references memory. By altering pointer values, they can redirect the program to execute malicious code or access restricted memory areas. These attacks are dangerous because they often bypass traditional security controls. They exploit the way memory is managed rather than breaking through external defenses. To defend against memory injection, developers should use secure coding practices, including proper input validation, bounds checking, and memory protection mechanisms. Operating systems should also support address space layout randomization and data execution prevention to make it harder for injected code to run. Next, let's discuss buffer overflow vulnerabilities. A buffer overflow happens when a program writes more data to a block of memory or buffer than it was designed to hold. When this occurs, the excess data can overwrite adjacent memory, leading to unpredictable behavior, including system crashes, data corruption, or even code execution. Attackers use buffer overflows to inject malicious code into the system. They craft input that overflows the buffer in a precise way, allowing them to take control of the execution flow. Once successful, they can run code with the privileges of the affected program. Buffer overflows are common in applications that do not properly check the size of user input. Languages like C and C++ are particularly vulnerable because they allow direct memory manipulation. In contrast, managed languages like Java and Python include built-in protections against such errors. A well-known buffer overflow case occurred in the early 2000s when a vulnerability in a widely used web server application allowed attackers to crash systems and run arbitrary code. The result was a fast-spreading worm that disrupted internet traffic around the world. To prevent buffer overflows, developers should use safer functions that enforce size limits, perform rigorous testing and code reviews, and use compiler-based protections such as stack canaries and non-executable stacks. End users and administrators should apply software patches promptly to close known vulnerabilities. Now let's move to race conditions. A race condition is a flaw that occurs when the behavior of software depends on the timing or sequence of events, and 2 or more operations attempt to access shared resources at the same time. If these operations are not properly synchronized, they can interfere with each other, leading to unexpected and often exploitable behavior. One common race condition is known as a time of check versus time of use vulnerability. This occurs when a system checks a condition, such as file permissions, but the state changes before the file is actually used. For example, an attacker may exploit a delay between when the system verifies that a user can access a file and when the file is opened, replacing the file with a malicious version in the interim. Race conditions are particularly dangerous in multi-venom or multi-threaded environments. Attackers can manipulate timing through automation, increasing their chances of success. Real-world incidents include privilege escalation exploits, where a non-administrative user gains root access by exploiting a timing gap in file or process management. To prevent race conditions, developers should use synchronization mechanisms like locks, semaphores, or atomic operations to control access to shared resources. They should also minimize the time between checks and actions and avoid relying on assumptions about execution order or timing. Finally, let's discuss malicious updates. These occur when attackers inject harmful code into software updates or when users are tricked into downloading updates from fraudulent sources. Because updates are typically trusted and executed with high privileges, they are an attractive target for attackers. In a malicious update attack, the attacker may compromise a vendor's server, sign an update with stolen credentials, or redirect users to a fake update site. Once the malicious update is installed, it may include backdoors, spyware, or ransomware, all running under the trusted identity of the software vendor. One of the most high-profile examples involved a legitimate software company whose update server was compromised. Attackers inserted malicious code into an update that was automatically pushed to customers. The result was a widespread compromise of enterprise systems, with attackers able to move laterally across networks using the trusted application as cover. To prevent malicious updates, organizations should implement secure update practices. This includes verifying digital signatures, using transport layer security for all update downloads, and hosting update servers in hardened environments. Users should be trained to avoid downloading updates from unofficial sources, and endpoint protection systems should scan updates for anomalous behavior even if they come from known vendors. As you prepare for the Security Plus exam, understand that application-level vulnerabilities like memory injection, buffer overflows, race conditions, and malicious updates are often invisible to casual inspection but carry serious risk. You may be asked to recognize the behavior or symptoms of these flaws in a given scenario, or to identify best practices for prevention and response. Focus on what causes each vulnerability, how it can be exploited, and the technical or procedural defenses that can be used to stop it. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.